Hello, everyone. I hope you and your families are doing well. My name is Farzad Inanlou, and I am CTO for radar and millimeter wave systems at GlobalFoundries Automotive Industrial Multi-Market IoT Strategic Business Unit. Today, I'll be talking to you about some of the ingredients that is needed to build a differentiated radar. For example, GlobalFoundries 22FTX is the only platform in the world with auto grade 1 reliability qualification and an FT higher than 350 gigahertz and an Fmax higher than 400 gigahertz. All right, let's dive right in. Here's an outline of my talk. First, I'll go over some of the trends and performance metrics when it comes to automotive radar. Then I'll talk about a top-level view of our offerings when it comes to our technologies. Then I'll do a little bit of an introduction on 22FTX, and I'll end on a slide on our automotive turnkey services. All right. So when it comes to radar, automotive radar, range, resolution, and field of view are three of the main performance requirements. When it comes to range, we'd like to increase that from where it is today to around 300 or 350 meters. That gives the car more time to detect and react at higher speeds. When it comes to angular resolution, we'd like to achieve an angular resolution of sub 1 degree, sub 0.5 degree, and that is really to be able to image the surrounding, similar to what LiDAR does. And this will help the car really detect, classify, track, and predict the movement of different targets. When you can image your surrounding, you will be able to tell the difference between a bicyclist, a person walking, a child, etc., and that will help predict that movement, and the car can make decisions based on that information. And when it comes to field of view, the goal is to cocoon the car in a 360-degree zone of protection. And this would mean increasing the number of radars per car up to 10 radars. So these radar system level, sensor level performances, right, are really driven by circuit level performances, and those circuit level performances are driven by transistor level performances. So for example, let's take range. When it comes to range, on a circuit level, in order to have higher range, we'd like to be able to pump more power out of the transmitter more efficiently and have that signal, of course, travel to the target, reflect back, and travel back, and then have our receiver, right, have enough sensitivity to pick up that signal, right? So on the transmitter side, for example, a TX P out efficiency, on the receiver side, the noise figure. And now this circuit level performance is driven by and enabled by transistor level performance, right? On the receiver side, for example, your NF-min, FT. On the transmitter side, Fmax, breakdown voltage, Vmax when it comes to reliability. And keep in mind, all of this has to happen. All of this performance for the radar has to happen while maintaining very small form factors given to the placement of the radar in the car, and also low power, because heat management and power management is also an issue. All right, so here are examples of how transistor level performance improvements on 22FTX compared to 28 bulk really translate to radar level performance improvement. Let's take angular resolution, for example. In order to achieve the goal of sub 0.5 degree angular resolution, what we need is on the order of more than 2,000 virtual MIMO channels. Now, this means on the order of 40 to 50 TX channels and 40 to 50 RX channels. Now, this raises concerns when it comes to power dissipation and heat management. And 22 FTX is 40% lower power, and also when it comes to digital processing, and 50% lower power when it comes to, and sorry, 50% higher PAE. I misspoke. When it comes to the output power on the transmitter, really contribute to alleviating these concerns for a high number of channels for high resolution radar. And really, this means that the transistor level performance improvements really contribute to being able to achieve our goal. Now, another example of this is really flicker noise, right? So flicker noise is also, when it comes to 22 FTX, 80% lower compared to 28 bulk. And this allows for better phase noise on the PLL, and also allows for better large signal noise figure on your receiver. Now, the good news is that this is 22 FTX is not the end of the story. Meaning, we are actively working to apply this mindset of how to improve transistor level, circuit level, in order to really enable market level and system level performances. And so we have roadmap items and roadmap technologies beyond 22 FTX that will really strengthen all of that. So please stay tuned for those as well. All right, so let's look at a top level view of our current offerings when it comes to mmWave SoCs for automotive applications. One of the things that makes GlobalFoundries unique is this complementary offerings in silicon germanium and also CMOS. So when it comes to SiGe, we have our 8HP and 8XP, and for CMOS, we have our 40LP and 22 FTX. And each of these really are well suited for specific area of the automotive mmWave applications and radar. And we are actively working to extend this beyond our current offerings on our roadmap items as well. I spoke about the CMOS in the previous slide. When it comes to SiGe, we are also working on roadmap items to extend really FMAX leadership beyond 600 gigahertz. All right, 22 FTX. I'd like to start with this slide, which is a press release that we did a few months ago with Bosch, who is actually using 22 FTX to build their own radar SoCs. And this is a huge testament really to how well suited 22 FTX is for mmWave SoCs, in this case, 80 gigahertz radars for automotive, Auto G1 qualified. Here's a look at what a FTSOI device in 22 FTX looks like, and I'd like to make a few points here. First, that the fully depleted channel and the thin buried oxide really contribute to the higher mobility and the lower loss, lower parasitics, which, all of this contributes to the higher RF and mmWave performance. Also, the backgate bias really provides a low resistance path to the bulk, and that really can be used as an additional design knob, additional flexibility in the design in order to boost the performance, processing performance, in order to reduce power, or even in order to have a non-signal path to the devices to do things like temperature compensation. All right, when it comes to the numbers, here is how 22FDX compares to 28 bulk. We talked a little bit about it in previous slides and linked them really to circuit level performance and radar level performance. And this is what the numbers actually look like. So on the left side, we see RF performance. On the right side, we see digital performance. And we can see FT 7% higher, 20% higher Fmax, 75% lower NF-min, 80% lower flicker noise. And as I mentioned, all of this translates to better performance at a circuit level as well. And when it comes to digital performance, we can see 30% better processing speed and 40% lower power. And as we covered before, when it comes to range, when it comes to resolution, all of these are very important. Now, here's an example of a benchmarking that we did for 22FDX versus 28 bulk for an ARM Cortex A53. Now, this is a common processor that is used in radar, and so as we can see, a total area reduction of 25%, total power reduction of 43%, and a performance boost of 11%. So across the board, superior performance really for 22FDX. So one of the other things that makes GlobalFoundries unique is that we have internal reference design teams that work on, in this case, mmWave example circuits, reference circuits that push the limit on performance. For example, in this case, 22FDX on a circuit level, while really maintaining and designing for reliability that is required for automotive. So in this case, this is an SoC that has 3 TX channels, a PLL, and an RX, and we can see really the performance that we can get from these circuits. For example, the PA more than 14 dBm at better than 15% efficiency. These are the numbers that meet and exceed what we're seeing in terms of requirements from radar design houses, right? Tier 2s, Tier 1s, and OEMs. And also when it comes to the PLL, the performance that we get, also when it comes to the RX. And this is just Gen 1 of our reference circuit. So we are actively working on Gen 2 of our reference circuits. And these circuits will be basically available and released, the Gen 2 circuits, later this year. And we provide these circuits really to our customers or these reference circuits to accelerate really their time to market. They use it as a starting point to accelerate the learning. And for example, let's look a little bit in more detail at the power amplifier. Here we see a power amplifier that is pumping out around 14 dBm. And we also see on the bottom right a really nice correlation between simulation and between measurements across different MPWs, right? Across different runs. And so as a result, we see a very stable process and great performance, great simulation measurement correlation. And on the left-hand side, we can see a really temperature behavior of the output of the PA across the band, across basically a temperature range of -20 to 125, that's 145 degrees. We see only ±1 dB of variation, which is for automotive, again, an important requirement to maintain performance across temperature variation. All right, so since we're talking about PAs, I would like to also point out some of the differences between FTSOI, which is a planar technology, and FinFET, which is a 3D technology, right? So first of all, higher FT, higher Fmax. And that FT and Fmax really is achieved at a lower current density, just due to the geometry. And the geometry also has reliability implications in terms of current handling, right? And more specifically, the fully depleted channel in an FTSOI, you can see it here in the middle cartoon. The fully depleted channel really results in the absence and the removal of the lateral bipolar, which as a result really extends the breakdown, the off-state breakdown voltage of the device by around half a volt compared to FinFET, which again, when you're trying to pump a lot of power out of a PA at 80 gigahertz reliably, auto grade 1, this is, and also efficiently, this becomes, this helps a lot. All right. Here is my final slide for today. And I'd like to end on a slide on our turnkey offerings. So, but before I do that, to summarize, today we've spoken about the things that really make, some of the things that make GlobalFoundries unique and really perfect for the automotive radar market. 22FDX, only auto G1 qualified platform today, with FT higher than 350, Fmax higher than 400. A roadmap that continues really these specific performance benefits for automotive radar, that is both the roadmap items, both in CMOS and silicon germanium, and really applies the mindset of what the radar market needs and how to translate that to specific offerings out of GlobalFoundries. And third item is our capabilities when it comes to reference designs and when it comes to having more, teams within GlobalFoundries that do these mmWave reference designs that really push performance, but also maintain automotive reliability in the circuit. That's the third point. And the fourth point is this slide, which is really GlobalFoundries is the only foundry in the world that offers production level 80 gigahertz test of the circuit, the chips, the SoCs, the MMICs, etc. And so you can see on this slide some of examples of some of that test and some of the packaging that we do as well at 80 gigahertz. And with that, I thank you for your time and hope sometime in the near future we will be able to have this session in person and meet in person and have fruitful discussions. But until then, nice to talk to you today. Bye-bye.